Hello, let me know if you can hear me and see me, and we'll start in just in a second. We'll cover quite a few topics today, and at the end we'll see some beautiful pictures in Tensorboard, and you will be able then from now on to have proper output of your data of the training results. At least in one way, because there are multiple ways that you should document your training results. Yeah, so let's start by just checking in the chat how many of you are actually active participants today. If there will not be any active participants, then basically I will just go in a lection style without trying to help you out. But it seems like that at least one person is active. So who is active today? Plus, please. Okay, so we have 2 people active today, so that's great. I mean, like, so you're a really privileged situation, because I think there at least RTU students are today busy with other things, and I contacted some of them that are good at this point in the course, that they have good results so far, and like the one that I'm talking about. So anyways, so she's going to join a little bit later. She's not out. So I see some of the names here also have potential of finishing the course. So I already in the Google Classroom I gave you some information regarding the problems of the results. So of the marks, the grades for the course, that like a lot of people most likely will not pass this course, and they already contacted universities, and they are okay with this, because they say that they are aware that students this year are a little bit more lazy and do not have success also in other courses. But I would not be happy to fail people. So please keep in mind you need to get at least those 40% or like so to barely pass. So please do not forget to do homeworks and work on them, and have questions in the chat here. So if you try to do the homework and it's not, something's not working, then send either email or like when we are doing the code online, so then engage with this. So that's just some comment on that note. So today we're going to start by doing some interesting stuff. We actually will have 2 parts. So first part will be, we will try to do fully convolutional neural network. So that will be something that it will help you out with the homework as well from previous time, because we will be able just to kind of build different kind of model from different kind of scheme, and in general just like make your life easier for that previous task. So let's see. So I think I will give a template just in a second in a 10.1 task. You need to wait a little bit. I had a lot of meetings today, that's why the template is not yet available, but it will be in just in a second. And by the way, if you have some questions regards to homework or some other stuff, you can try ask those questions. And meanwhile, I will prepare the template. So this will be template for fully convolutional neural network, and we will talk about this in a second. And they will also talk about multiple things that will be also included in this this code. So I mean, the homework included the maxpool function, but we did not talk actually before together. So that was something new, and we will use that one as well today, and we will use some other things as well today. So just in a second I will give you the template, and we will change it a little bit with regards to the model, and we will understand together why we are changing it. So I'm adding right now the task 10.1 in the Google Classroom, and I will also post the template in the Mega Drive just in a second. So this will be complete FCN based on video tutorial. That will be just a second, and we will start. And meanwhile, you can also install on your Conda environment the TensorFlow. So we will not use the TensorFlow itself, but we will use the Tensorboard that is a part of TensorFlow. So that is a specific type of program that is included in TensorFlow that is really nice. Basically, the PyTorch is right now missing. So the PyTorch has the Wisdom program and some other stuff, but they don't have the kind of interface where you can develop and test and evaluate your results. This is something that TensorFlow has. So please try to install that one as well. I will just give you a second the command how to install it. And now I opened also the 10.1 template. So that is available, and I will look at chat in a second as well. So the 10.1 template for fully convolutional model is available. And I will also share this template here in the chat as well. Yes, that's right. I see in the chat the question about the grade. Yes, the grade will be exactly the score of the Google Classroom. So I already agreed with universities that that's okay how to measure the score, because this is like a practical work combined with the classes, and basically, as you know, the practical work in our course is quite important, and we don't like baby feed everything, so you need to work on your own as well, and that's the only way how you actually learn, when you try to solve some puzzles your own. So that's right. Just a second, so let's start adding some of the things. So you need to install, I will add this one here on the Jamboard. So you need to install TensorFlow, so pip install TensorFlow. I know you can install it also from Conda, but just to be safe, that there's that is just the simple TensorFlow without any like GPU versions and other like interesting compilations. I'm just like I think you can install from, like, you can decide, you can install also from Conda. Actually, Conda is great because it also installs all of the dependencies. Like, for example, if you would install some library that uses FFmpeg, it would also install on your computer FFmpeg without needing to install separate software. So that's why Conda is great. But you can install with pip this one, and that should work. So just a second. So that will be needed for the second part of today's session. And please get the template ready. So I will ask in chat, is template ready for work? So plus minus if there is some problem. So that's with the template. And I will try to find if I'm having everything that I need here on the Jamboard. Maybe I need something else with regards to installation. All right, we need something else as well. I forgot. Okay, so, but that's fine. You can do all of this at once. So you need to install actually 3 packages. So you need to install TensorFlow, the Tensorboard X. So that is a library that allows to connect PyTorch with TensorFlow. And you need to install argparse. So the argparse library is really great way to pass the hyperparameters, because right now we are passing hyperparameters as a constant in our code, and that's really not optimal. You should not like pass hyperparameters as a constant in your code, because hyperparameters you cannot guess them, you need to find them. So, and when you do the grid search, like it will take a time, like many runs, and that's why you should do that one like using arguments. So let me now quickly share the code that will try to show you how to install those libraries on the PyCharm if you're using that ID, development environment. If you use some other development environment, then you might be needed to go to console and look for the your correct environment. So if you use this environment, then you can do the Python console. Here the button, like in the bottom there is a button here, Python console. I mean not console but terminal, sorry. Terminal, so it shows the current environment. So that's our environment, that's what we need. And here you can write pip install arg parse and those others libraries, and then when you press enter, it installs that library for your environment. So in my case, I updated just argparse or whatever. So do that please as well from the Jamboard here, and in a second we'll talk about a few things with regards to convolutional networks, fully convolutional networks. Yesterday we implemented our own kernel function for fully convolutional for convolutional network for ConvNet, and you should now understand how in general it works. And today we will look at very specific case of ConvNet. By the way, there's a lot of material with ConvNets. I could talk about that for many sessions, but right now we're limited in time, so we need to also cover the other part. And I'm just thinking that there is some parts that we should look at that today. So please install those libraries. So let's ask what libs installed. Plus minus. If there is some problem, you can type in what problem you have. So nice to see in the chat actually multiple active members of the course. That's really encouraging. So thank you for joining online, and hopefully it will be fun today. So let's start talking first with that fully convolutional stuff. So let me add quickly a few things. So yesterday we made a model that is, so just a second, my notes hanged up a little bit, but no worries, everything is under control. So yesterday we made a model that we need to calculate the width and height at the end of the convolutional neural model, right? So remember we used the formula to calculate what will be the change of the width and height in between layers. So at the end, we would know what should be the shape that goes into final linear layer, right? So we use this formula, right? And this model is fixed to very particular input size. So the input size is always 128 by 128. And if we insert here 28 and pass through all of these layers, at the end we have some n out that we can flatten and give the linear layer and then do the softmax and classification. So this is like very simple ConvNet, right? So this is this. And in your task that I just published as a 10.1, we have something different there. So the task that I published there, it looks like this. And I also maybe should share that one, but yeah, it will be, so you can probably zoom in to look at a little bit closer. So we have some additional items there, but the main thing actually here is that this one is fully convolutional network, FCN, fully convolutional network, ConvNet, fully convolutional ConvNet. So the difference here, the main difference is that the input can be any size. So the input can be B1, and the size can be like width and height. It can be either like a portrait, it can be a square, it can be anything, and basically we don't need to use anymore this formula. So let me illustratively show you what I mean by that. Is that if I add this formula here for this network, we don't care anymore about these n out and all of these parameters, like what is the shape. We don't need this at all for this model. But it comes with some drawbacks as well. So it's really nice that we can have any type of input, like the image can be low resolution, high resolution, whatever. Like there is limits. So if you train everything just on, so it's impossible to see the layers, but the same model is added also in Google Classroom, by the way, for the 10.1 assignment. And I will also share it just in a second in Mega. So if somebody don't have access to the classroom, just in a second. So I will give you the link in Mega just in a second. But yeah, I agree that I sometimes make a little bit too long these sausages of the models. I should split them in multiple columns. I will do that for the next sessions. So here I have in Mega that image if you want to have access to that. So the one benefit, great benefit, is any input dimensions, so we achieve this great benefit by using this particular formula. So sorry, so we are getting this by using the adaptive average pooling, or actually, if you know that you can do the wait a second, there's something. Here this adaptive average pooling, it's actually simple average pooling. It can be actually also max pool. It can be any kind of pooling operation, and we will look at that in just in a second. So the idea is that this is a way how we can reduce the dimensionality, in this case the output dimension. So the output size is the batch, the channels out, 1,1. Basically, we are reducing all of our outputs to like, there's actually multiple methods how we can reduce it, but one is like this, where we would reduce it to 1 by 1 pixel matrix with a depth of C channels out, and then this is always the same regardless of any input. So the only limitation is that if this is too deep and the resolution is too low, then it will fail. There will be error because we cannot reduce at some convolution the size. But basically this works great because there is no need of fixed sizes like for the last layers. So that's a good news here. But also there are some negative things. So if you imagine if there is something that works for any size, so that means that it definitely kind of pays attention to details that are not really in a context. So the details can be in a small image, in large image, and that's what we use for classification. So the case is for the fully convolutional networks, that the model will predict the, for example, if we try to predict if this is a face, the model will think that this is a face in both scenarios. So let's see, so the FCN would think that this is a face also, because there are the main characteristics for the face in the image, but they are not connected in any like hierarchical way at the end. Like there is some like a limited hierarchy. So if you make your FCN very deep, it might be possible that you would avoid this, but like for shallow networks, this would classify as face. But for the normal ConvNets where you have the defined resolutions, so and no pooling at the end, so this would be the case, and also for FCN also this would work. So that's an interesting feature. Sometimes it works good, like for example if you have fully convolutional networks for semantic segmentation, where you want just to identify if in this image there is like some like segment that is small, like I don't know, like not reasonably small, like there is seeing the silhouette of human being walking or something like that, and this is like 10% of the image or like 20% of the image, and the depth is enough, so maybe we don't need at the end proper like connection for the fully connected layer, and this would work. So there is one guy asking for a small break. I cannot take 2 minutes definitely, but so I'm forced a little bit just to have a small second to like just a pause. So please sorry for this pause, but I will be back just in hopefully in 1 minute. Meanwhile, you could look at the code and like think about some questions. Just a second. Sorry, one of my business partners interrupted us. Really sorry for that. Anyways, it's gonna be good now. So anyways, so here we have some interesting, I don't see any like additional questions, so we will proceed with our program. So we have some layers that we have not yet looked at it. So there is a leaky ReLU, then there is a batch norm, then there is a adaptive average pooling and some kind of average pooling. So we will look briefly at those and then we'll do the coding. So the leaky ReLU, this is something that we already talked in some other session. So the idea is that the ReLU is a problem that it can be a dead ReLU, so the dead neuron, right? So the dead neuron happens when the input of the function of this nonlinearity function is in minus, and if you remember the derivative that you coded yourself, then all of the derivatives that are here in this minus part, they are not moving out of that value. So we have dead neuron. There is the zeros come in, zeros come out, nothing changes. So the one way that is kind of a little bit better is a leaky ReLU, where you have a slight slope in this part, so that if there is some potential of learning something, it would still like slowly go either in that direction or stay the same place where it was. So the leaky ReLU is a little bit better, but at the same time, don't be too excited about the functions. The activization functions is like one of the low-hanging fruits that all of the researchers already have looked many times, and over the years there were no like significant improvements with these. There are some GELU, ReLU, all sorts of functions like parametric ReLUs, and like at the end, it's the deeper model is, the less effect of this there like has. So the ReLU, the simple ReLU, the leaky ReLU, those are the best options right now. So for some cases, max out could be a really interesting option. So if you look at max out, where it is, it's actually like multiple kind of linear layers chained together with the max function. So this is actually the max out function itself is a universal function approximator, and the neural model is also the same thing. So I have seen some models that reduce the depth by adding at the end the max out. So that's one option, but at the same time, not really convinced about the effectiveness. So this is one that we'll use, the leaky ReLU. The derivative for leaky ReLU also a really simple one. You could probably implement that one. So that's one part. Then the other part is that already we were talking, that I added for the homework, is the pooling operations. So there are multiple types of pooling operations that you can think yourself. Interesting pooling operations, like for example, probably you could build some kind of something similar to like median pooling operations. So is there any reason to use ReLU over leaky ReLU? That's fun question actually. Gintz is asking a good question. So from performance perspective, right? How fast the mathematical operations happen, the ReLU and leaky ReLU should be quite the same. Like there's just maybe like almost I think should be no difference. I think like leaky ReLU I guess is probably a little bit safer way to go. So they need initialization of the modern neural networks kind of avoids the problem of dead neurons in most cases. But if the initialization is so bad, then leaky ReLU can help definitely. So you can imagine if you initialize your weights as zeros, then when you have only ReLUs, then everything is dead. So anyway, that's a good question, really interesting. So then the pooling operations. So these again are functions. So these are really dumb, simple functions. So one simple function is to use the max pool. So that means that, for example, if you have like it's actually used normally in the kernel size and stride terms of the way how you define the max pools. So here it says that there is a 2x2 filters with stride of 2. So you say I want 2x2 elements and stride of 2. By the way, so the 2x2 elements are jumping by two cells. So it can be something else as well. It can be, let's say, 2x2 elements and the stride of 1. So it's just jumping one by one. It's also a good way maybe sometimes. So there's no specific limits, but the idea is that you would select the maximum value from that region. You can also do the same, as I said in this model that we will do, the average pooling. So the average value is the average pooling. And you can also choose about which dimension do you do this, because in this case this is x and y, right, width and height, but you can do also the same operation over the depth, so it doesn't matter like basically in which dimension you do this. And the rationale, the thinking of the why would you do this is one, if you imagine in this image you have, let's say you want to classify dog, and the dog is right now located in this green area, and the neurons excite and give the like the feedback that in this part there might be a dog, and this is really high value here. So we can select by maximum that we only pay attention to that area and don't pay attention to other areas. So that's one explanation. And the other explanation is rationale is that we want to compress the information, and we want our model at the end not to have the same input, same like a size input as in beginning, and work with something less dimensional. So you can imagine by reducing downsampling, reducing that also works. By the way, also there are some other ways. You can use also bilinear downsampling, and trilinear, bilinear, all sorts of those fancy ways to do the downsampling, and also upsampling, of course, with two L's, I think, or maybe I think I misspell it. Second. So some of the more modern models actually use these a lot. So like if you use any like kind of downsampling function that can be then derived, like tractable, that we can calculate derivative, that would work. And basically like the bilinear downsampling, upsampling, and all sorts of those things sometimes even get even better results than simple functions. So depends on the data set, the resolution, the quality, the cleanness of the data set and stuff. So this is another function we will use. So the third function that we will use is the normalization function. So I will introduce you also with more powerful normalization functions. So normalization. So the idea is that the rationale here is that we have some kind of input. So for example, we have two channels input, so for some layer, right? So this will be, let's say, from convolution layer 1 to convolution layer 2. We have, let's say, channel 1 and channel 2. And these two channel information of the data points, this is something that eats the next convolution, right? So, and here we have, for example, the data like of the dog or something located around here. So all of our data is located around here for this particular batch. Because you remember, we train everything on batches, right? So our first batch, like unfortunately, all of our dogs are a little bit on one side of the data set or whatever, or they look, all of them are fat, but there are also skinny dogs or something like that. So all of our data is a little bit the channel information is kind of off the center. And if you remember the ReLU and leaky ReLU, right? They don't like information that is distributed like this. Especially nice to see that on leaky relu, where there is like classic, like the slope that you can recover also. So what we want to do is that we want our internal representations of data to be centered around 0, somewhere like here. And that we do with the normalization. So we pass our internal representations of these channel data, right? That is not something that you can look as a human and understand, but this is like kind of the internal representation. We want that to be around centered, around 0. But the problem is that we're working with batches, right? We don't know what is the true center, or like what should be like what should we divide it, how we should move it, like translate it and stuff like that. So the only way how to do that is to learn. So we need to learn from each of our batches what is our like standard deviation, what is our mean value. So we need to learn that, and the way how to learn that is using batch norm. So this is one of the old, it's not the oldest one, but one of the oldest ways how to do this. So the batch norm. If you look at AlexNet, they have like funny older version of normalization. Nobody uses that anymore. So the batch norm is something that a lot of models still use, but this is not anymore the state-of-the-art approach. So the idea is that we have some learnable parameters in this function. I believe that some of you can implement this function by hand right now yourselves, because as you see here, there is a gamma and beta. Those are the learnable parameters. So maybe I can like mark it. So gamma and beta, those are learnable parameters. Everything else is calculated from the mini batch. So from mini batch, you look at these x's, you calculate the mean, right, the mu. Then you calculate the standard deviation, square it to have the variance. Then you subtract it. Then you divide it. So this is just like absolute or something. And then you like shift it a little bit using the linear projection of the learned linear projection, basically. So it is actually some small calculation applied with the linear projection. So that's it. That's what it is. So really simple procedure to solve this problem, so that basically we would learn what is the approximate shift of data in between convolutions in order to move data around 0. So that this operation we can do easily ourselves with the input data, right? But we cannot do this easily ourselves with the deeper layers. The deeper layers then would require us to like process the whole data set every time anything changes. That is like not reasonable at all. So that's one thing. Now let me show you also the state-of-art approach, and then we'll start coding this stuff. So the state-of-art approach would be to use something called group norm. So the group norm is a generalization of instance norm and layer norm. And there are some visualizations. So the function and algorithm do not change a lot. The only thing that changes is the dimensions on which we watch the dimensions that we use in the calculations. Sorry. So here there's some examples, and I will try to make them even more simpler. So the group norm, and we will I will probably ask to do the group norm in a homework probably, because the group norm is also implemented in PyTorch. It's easy to use. It's just need to understand how to use it. So group norm is the generalization of layer norm and instance norm. The layer norm is advised to use with RNNs, LSTMs. So this is really popular with those models and gives quite a dramatical boost. So the instance norm is popular with GANs and also like some other models. And the group norm is basically the kind of generalization in between of both of them. You can get both of them from same function. So, and the way how it works is the following. So the batch norm is a lot different than these, because you can see that the n is the batch and the blue ones are here like on this direction, and all of these are in another direction. So I will try to explain it step by step, and if you don't understand something, please write in the chat, and also for the other things so far that I explained. So here, the idea for the batch norm, I will try to make them like in order as they are on those boxes here. So the batch norm works by having, so if we have some images RGB, right? So red, green, blue. So this will be red, there will be green, there will be blue channel, and these will be our kind of inputs, for example, but they might be also some internal representations. So let me see, can I copy them all? I should be able to do this. Let's see. If I will not be able to do this, then I will show you that in other way. It seems like that I cannot do this, unfortunately, in this way, but I will show you then in full screen with the sketch. So I think it's kind of important to understand the mechanics of these normalization methods. I hope you understood why we need them at all, because we want to center our data around 0, right? That is beneficial. As you've seen in your homeworks, that when you start centering data around 0, you get better results also for regression, classification, and other tasks. So here, let's see, so we'll try to draw this with this one. So we have red, we have green, and we'll have the blue colors, and this is basically one sample. Okay, so we have in the batch we have multiple samples like these. So this is one sample in a batch, and imagine that we have batch size 3. Okay, so batch size 3. So in this case, with the batch norm, so let's add here some statement up there. So this will be batch norm, and we'll also do these. Maybe I can copy all of this some other times as well, so I don't need to do this later. Check. Definitely, probably not the most efficient way to do this, but on the whiteboard it will be easier. So if you know some better tools to draw live sessions, you can send me some information. So like this, and this, and this. So the representations before that you saw on the slides, they are sometimes not really good, like to understand what is actually going on. With these, hopefully you will. So there is also a layer norm, and there was also instance norm, and there is also a group norm. That is generalization of the previous two. So here, the way how we center our data for the batch norm, that's happening by per channel basis. So for the batch norm, we need to define what is the number of channels. So, and we look at the batches. So maybe we should add also here information. So batch size is 3. So we look at the batches. If there is a batch size of 1, then batch norm fails. So that's something that you need to be very careful about. So here we calculate this around this channel. So for all of the pixels in this channel, between all of these 3 samples, we look at all of these 3 blue boxes, 3 blue maps, and calculate the mean and variance, and then shift those pixel values. Then we do the same also for the green ones. So for each of these, like the batch. Then we do also for the red ones, and we learn what is the mean and variance of approximately for whole data set. but this is batch size dependent. So if we increase the batch size, we will have better results. This is something that is shown in many research already. When you have the batch norm, you should have the largest number of possible for the batch, because then you will have much more stable convergence. If you use the some other these methods, they are not batch size dependent. So the other method is then to use the layer norm, where we look at each of these separately. So we don't care about anymore about the batch size, but we calculate the mean and standard deviation between all of the red, green, blue values. And we subtract and move them around for each of the samples separately for each of those maps. They take the average from all of them and then subtract from each of them. So, and in this case, this is done for every sample in the batch, so you don't care if you have 100 batch samples or just one, it will work the same way. At the same time, of course, the learning procedure is again for the whole dataset, so that means that the larger batch size you get, you will still have a little bit better convergence, but that is not so connected with batch size as the batch norm. So that's another way. So then another way is to calculate just for every map separately, like that, for every sample separately and for every map separately, like that. And you can imagine that the next way is that we can define how many channels we want to combine. So the group norm says that we can combine, let's say, so we can learn, actually, it is learnable. So I mean, it will learn that we should combine the red and green together and leave the blue channel separately. So combine red and green, blue separately. And maybe in some other case, it will learn that he should combine the red and green and leave the red separately. So that's also possible. So again, it will combine these two and leave this separately. And the logic here is really nice, because the group norm actually means that, for example, if you have some classifier that needs to classify I don't know, some kind of penguins or something. So the penguins are always more a little, maybe they are black or okay, that was bad example. And then let me see. So what kind of animal? So I don't know, let's see. So we need to classify some kind of red balls, for example. So the red balls are on the field, for example, and the red balls are always on the red channel, but the green field and the blue sky is not important. So the green field and blue sky is not important, and that's why they can be combined as one type of features, and the red balls could be defined with the other type of features. And this is something that model learns itself. It automatically, basically by the gradient descent, decides that in this hyperspace of gradients, that part is optimal for, the separation of that channel is optimal for detecting red balls, and combining those other two channels is optimal for ignoring the sky and green grass. So I hope that makes sense. I don't know why the penguins came up in my ideas. So is it clear so far? Is it clear so far about the functions, about the new functions that we will use, plus, minus? And if something is not clear about these functions that I just described, so this makes sense probably more if you did the previous tutorial and homework, because we talked already about the convolutions there and how they work, and about the channels and the batches and everything. So please let me know in the chat, does this make sense, and do you get it so far? And then we'll do the coding finally. Okay, great. I see one plus. Let's see. By the way, if it's not a plus for you, then it would be great to hear a little bit of like question in what direction. Okay, I see two pluses. Hopefully, I really hope that it makes sense. So there is a group norms. So this is a normalization. So shifting the values, right? Then we have the pooling layer. So this is reducing the size along some specified dimension. And then we have the activization functions, like those that are a little bit different than before. And the fully convolutional network, that means that we don't need to calculate the exact number of the output features, and we just average pool them based on the input, and then just pass it through either to the linear layer, or to make it truly fully convolutional model, we can like reduce the average pool to actual number of the classes to 10 classes. So for example, if we have the last output channels as 10 classes, then we can average that down to that one. So maybe we should do the truly fully convolutional model together. So let's do the code. I kind of forgot about this nuance, so sorry for that, but that will be fun. So here, let's see. I will need to quickly find. So this is a template from yesterday. I just deleted some parts of it. So here there is the model that we will now code together. And by the way, this code will be quite similar to what you need to do for homework, at the same time a little bit different. And I think I will make the version that I just described to you, that is fully convolutional. I kind of don't know why did I left the linear layer at the end. So anyways, if you have some questions while we code that, also don't be shy, try to ask. We'll show you some stuff. It will be interesting. So hopefully. So we have the encoder. So this code that I'm just making, it should work also immediately on the Google Colab on the GPU, and hopefully it will we can run it today. So one thing we can do is delete the get out size, because we don't need anymore to calculate what will be the out size. So that's a quite interesting difference. We can also delete fully connected layer. So I just want to emphasize that that's quite a fun thing. So we could leave the fully connected layer there and make it not really truly fully convolutional. I will later update also that scheme that I posted on the Jamboard, because I kind of did not see that I have the linear layer then. But it doesn't change that much the model, because there will be still the average pooling and stuff. So we have the model here. So let's start writing it. So torch. So and this model we will see that works on different sizes of the images. So that will be fun as well. So so there will be the in channels, as in the image that I shared. So the in channels will be 1. Of course, the out channels will be 8, as it's written. By the way, let's make it a little bit different. I will later update this scheme. So if you make it as I asked on this scheme, I will give you 100 points anyway. But basically, I just want to make it a little bit more interesting. So let's say that this will be to the channels 4. Then stride will be 2. Then padding we want to. So the kernel, I forgot about the kernel. Sorry. So the nice way to write would be to break a new lines here, like that. So then the kernel size will be 5. The in channels, by the way, I'm really chaotic today. Sorry for that. I didn't have time to eat, that's why. So the channel stride padding 1, right, like that. So normally the first layer is with larger kernel size, and then when you go deeper, then you reduce the kernel size. So then the next one we can add there's no like defined order, but we could theoretically add here the batch norm. I know that was not also in the scheme. The scheme, the batch norm goes after. So the scheme, I mean like the batch norm location, there are some papers that suggest it's better to put it after or before ReLU. So again, everything becomes less important the deeper model you have. If you have shallow model, then it's a little bit more important. If you have deep model, then you actually don't care about the order that much. So here, for deep models, you even don't need biases anymore. You can just set like here is an additional parameter like bias false. So for deep models, you set everywhere bias false, and there is a research that shows that like it doesn't matter if you have bias or not, because deep models can have the same effect as if there would be a bias. So okay. So the number of channels here is the outputs 4. Then we'll have the torch and leaky ReLU. And the leaky ReLU default parameter is the negative slope is 0.01, but that doesn't matter right now that much. So then we copy this block. Let's say copy this block 3 times, I think, or something. So we can copy it, let's say, once. And here, when we copy the once, I suggest that you change so the in channels now should be 4, the out channels should be 8, and the kernel size should be, let's say, 3. So let's like make it a little bit smaller. By the way, okay, let's leave it like that, but I will show you for the next layer also really useful thing. So again, so let's see, there will be another layer here. And then the second, I will copy these values also in the Jamboard. By the way, I have to write them in one line, but please don't do that in your code just because I don't want to fit all of this in one screen. For your own code, I highly advise to split it in multiple lines. The code must be readable. Like the spaghetti code is not optimal anytime. So don't do the spaghetti here. So the real spaghetti is when you start writing a function and function and function and function, and then also do not add any parameter names, then it's like real spaghetti. So that is bad code. So like that. Kernel size, stride, padding, cool stuff. Features, ReLU. Okay, so let's see. We have 4 to 8. Now 8 to 10. So we have 10 output classes. That's why 10 here. So do we have some parameters? No. So 10 output classes. And here I want to show you this nice thing that there we have 3 kernel size, stride 1, padding 1. So this combination is super common. This is a very popular combination because this combination ensures that the input size is the same as the output size. So you can have this combination like thousands of times, and it will not change the width and height of the feature maps. So it's like very popular thing. So we can use that one. Then let me think. So I think basically what we could do is we could just add an additional one convolution at the end that will again do nothing in terms of changing the channels or the size. And then we can add torch and adaptive average pooling. So the adaptive average pooling is basically the same thing as just an average pooling, but it gives additional benefit of avoiding to calculate the kernel and stride in a forward pass, because depending on x, we can calculate kernel and stride and reduce the dimension of the output as we want. But so there is an automatic function already for that. And there was something else that I forgot, but still. So output size 1 by 1. The thing that I forgot is that the adaptive average pooling do not have any learnable parameters. So we could even skip it out of the encoder and everything would work anyways. So the learnable parameters, the parameters that we want to learn, are only included in the red parts in my schema that I gave in the task and also here. So this is learnable. So the batch norm also learnable. The leaky relu not learnable. So there is nothing that you can learn in the leaky relu function. Like if we leave it out here, if we delete it here and just add some kind of function in forward pass, everything works great. Like it's not something that we need to define it and then it's fixed. So also here, of course, this is learnable like it was, and the adaptive average pooling also not learnable because there is no kernel or something that we learn. There is just an operation, very simple algorithm that reduces the size. That's it. So hopefully that makes sense so far, but we'll see that in just in a second. So then here, let's see. So there will be the some kind of out, let's say, of the encoder, forward of the X, and the out of the encoder is actually now in the shape, so I can add some of the shapes so it makes clearer. So shape here is the batch, 1, 28, 28, and here, regardless of any size, basically also here the size can be anything actually, width or height, except this, if the size is too small, then there will be error because the stride cannot execute. So, but large images will work always. So here the output then is 10 by 1 by 1, and we need to predict 10 classes, right? So very easy stuff now. We just need to change the shape here. So the out is then the VeA of, so we can make it so -1 by 10. So this is exactly the same as if I would write the same line as, maybe I should write multiple ways that could hopefully make you a sense what it is. So X size 0, so that means the shape of the batch here, so the batch size here, so this is the same as this line, this is the same as this line. In most cases this is also the same as this line, so batch size. But in some cases it's not the case. For example, in the production version or on the last batch where you don't have full batch size, maybe it will fail. So that's why we should not use the constant here. And the -1 means just the rest of everything. So I mean, also this can be the same as -1 like that, and so on. So all of these lines mean exactly the same thing. So hopefully it makes sense. If it doesn't make sense or you don't understand something, then please write in the chat. So I will add this to the Jamboard and make sure that everything works. Just a second, should run it, test it, and if it works, I will add it in Jamboard. So I'm trying to run it. Okay, there is a problem here. Sorry for that. Let me check. I did some problem. Okay, so the problem is very simple one. Here there is missing 10 features, of course, because we cannot give the batch norm some features that are not defined, like that are more than we defined. Now it works, so great. So it works, and I will add this quickly to the Jamboard. So this is a truly fully convolutional network, no linear layers whatsoever. And I will later update also the task and the Jamboard because I kind of did not see that in my image I have linear layer at the end. Sorry for that. So I'm adding this inside the slide number 7, this piece of code. Make sure that it works for you locally, and then we'll run this on Google Colab. If you have GPU on your computer, then maybe you should go up in the first lines here and comment this line of maximum length, because otherwise it will just run the whole data set. But I don't want to run the whole data set, so that's why I have this condition for the CPU. So, and also, just a second, I will show you in the Jamboard. So the code is now located here on the Jamboard. And let me ask in the chat before moving to the next task, is it clear so far and working for you? Plus, minus, and if it's minus, then please be so kind and write some comment of what's not clear in with regards to this model. And with the syntax or something else, I'm happy to explain. So I will wait a little bit. And then you submit the code for the task and you get 100 points for the course. So that's a good thing. So those of you finished, you can try to run this on Google Colab as well to see what is the result. This model is really weak model because, as you see, there's like very few layers. If you want to make it stronger, you can add extra layers that do not change the size, for example. Or you can also, of course, add some extra layers that change the size. So what I suggest is adding some layers that do not change the size by 3 by 1 by 1 convolutions in between those strides, right? The stride convolutions, you can do that, or like just make it deeper. So the question, I wanted to make my network, how would I go picking out parameters used? Basically, what would I design the scheme begin as? So the schemes for the models, that's something that I will give you for the homework. For the homework, I will give you a template for Torch Vision model. So the Torch Vision, the library Torch Vision, and also basically there are a lot of model zoos. They are called model zoos. The idea is that there are like kind of classic models, classic model architectures that are proven to be good. Okay, funny, this doesn't work. Torch Vision library didn't work. I mean the website. So I guess I cannot show you that one. Let's see. Anyways, so there are some models like ResNet, VGG, DenseNet, all sorts of nice models over here as well, AlexNet, SqueezeNet, InceptionNet. So these are architectures that are kind of proven to be good. You can definitely do your own architecture, and we will do that in following sessions. Depending on specific needs, you can adjust it. So in like a full course that I do also in other universities, I go in depth in most of them. So, but here, like I don't have time to explore these architectures, so there are some like rules for those. So I would advise, as in homework, you will see to use pre-trained ones and then work on them. Also, sometimes you want to change them because most of them are using this old school batch norm. Maybe you want to use group norm. So, but that's a good question. So anyways, it's not really a silly question. That's, I think, is good. So I see 2 people active. I really hope that other people also will catch up. And meanwhile, I will try to do the Google Colab. So the way how you do this on Google Colab, if you don't have access to GPU, also remember that university gives access to GPU as well. If you don't know how to access it, you can let me know. So here, the way how to access GPU for free is go inside Google Colab, choose here the runtime to GPU, and then copy your code, because right now all of our code is just in one file. That's why it's easy to copy it here, and then press run. And now it should work. First of all, it's connecting, and after it's connected, it will work on whole data set using these parameters and using our fully convolutional model. The other way how to test if this is a really fully convolutional model would be to increase the size of X here. So that's another thing that I will add for the template for those that will do this homework later, or not homework, but this class work later. So those who submit this work now, you're lucky, you will get points, and this will be great. But for those who will later, I will add here a small code that will increase randomly the size of X. So it should work always with different sizes of X regardless of the size. So let's see. So after the first epoch we got n. So I forgot one important thing again. I did this yesterday already and nobody corrected me. So I guess somebody who was here yesterday knows what is the problem. That's a fun thing. So let me show you. Of course, we are doing classification, right? The classification do not work if we, at the end, do not have some limiting factor for the probability distribution. So the limiting factor in this case is the function that ensures that the sum of probabilities is 100%, and also so this is a softmax over dimension of 1, and I will update Jamboard. So the idea is that the cross entropy wants to have one hot encoded values, and the softmax is the closest tractable function. There is also some alternatives, but one of the closest ones that would give us one hot encoded vectors, or basically probabilities that are either zeros or 100%. So that's something that we would use here to avoid the logarithm out of 0, or some like really large numbers, or all sorts of interesting things. So, or negatives or something. So please fix that part of the code. If you run it already, probably you came across this problem. So now if I go back to the Google Colab, if I copy the code again, the updated version, run it. So one thing was really fun that you saw how fast it was. Like yesterday when we coded and tried to run on Google Colab our own convolutional network that we coded from by hand from very scratch, like using the kernel function and everything. So that was really slow, but this one works like really fast. And after the first epoch, we already get the 47% training accuracy with really simple model, fully convolutional, and probably it will grow higher, hopefully. 65% looks good. So, okay, I don't want to spend too much time on this anymore. So this is kind of fun thing to do and finish and get points for this. Now let's move on to the Tensorboard tutorial part. So the Tensorboard, let me show you how it works. So the Tensorboard is a tool that helps you to I will show you just in a second. So this tool helps you to display your results, to aggregate your results, to do a lot of things with regards to your results. Also, with the template that I gave you, so the template, just a second, Tensorboard template, there is, there is a bug here, sorry. So first of all, you need to import Tensorboard utils, just like that, without defining that import from the file. So the Tensorboard utils will be other file that I give you with this template included. If you see, there is two files, the Tensorboard and Tensorboard utils. So the Tensorboard utils is like a small library that we made that is avoiding bug that nice TensorFlow developers have not yet fixed for I think about a year or so. So the problem is with the H params, so that there is a specific function where you can compare hyperparameters, and if you don't use this fix, you will create a lot of unnecessary data records in your Tensorboard. So that's one thing. Then I will quickly show you the benefits of it, and then we'll code it. So the benefits are the following. So first, we will pass all of our parameters as arguments. So we will give the run name, sequence name. We will also give the learning rate, for example. So add more parameters. We can do that here. So learning rate. So the learning rate we can give as something by default. So E minus 4, and this will be a floating point value. We can also give, let's say, batch size. So this will be by default 32. And again, I must stress this. I sometimes see students thinking that they will make these models and run once and everything works. So this is not the way how it happens. You need to find the correct hyperparameters for every specific dataset, model, the case for everything. So here there will be then how you access your learning rate, for example, is by using this syntax. So the arguments, so let's say learning rate will be inside args dot learning rate and also dot batch size and so on. So that's really nice way to pass parameters from console, and I will show you how to do that. So I will drop this on Jamboard just in a second on the 8th slide. And the way how you would do this, if I open the terminal here, and if I look at my Tensorboard template, so 10.1 Tensorboard. Okay, it doesn't give me the output, unfortunately. That was not what I expected. Just a second, I need to move my location of directory to the correct position. So let's see, so Python, so Python, then the 10.1. So all of these deep learning models, you usually run them from console. You never run them from any like GUIs and stuff like that. So here there is the learning rate, and we could test it like if it was E-4, we can test it E-3. Then let's say batch size, we can test 16 and so on. And if we run this line, it would produce the result. And let me also then try to run like finished version, and we'll see what happens. So if I run it, okay, the problem is that there's include missing. I will fix that just in a second. And meanwhile, add this to the Jamboard. So, and I also asked the question in the chat. So, is the argparse function understood? Plus minus. Do you understand what is the benefit of using argparse for hyperparameters and how to use it? So that's my question. Meanwhile, I will fix quickly the problem with the import. And sorry for adding those small problems in the code. I will make sure the next time we don't have those. So my cursor is not shown. Just a second. So let's see. Can I run it again? Okay, it seems like it's running, hopefully. Something at least is working. Not sure exactly. So, okay, it's working, I guess. Okay, let's kill it. Can I kill it? So what about the chat? So I see one person saying that he understands the benefit of using arguments, because we need to search many types of hyperparameters. We need to kind of find which are the best ones, right? So that's the reason for it. Would be interesting to see if others also understand it, or if there is some question, please ask it. It seems like that my console kind of little bit died, but that's no problem. That's funny, I cannot do anything with this. So let's see again, let's try again. Okay, so cd in this, then run. So Python, then what was the name of my stuff? So 10.1 Tensorboard, finished. Then we can pass, let's say, batch size 8 or something, run it. Really hope this time it works. I'm not sure exactly what was there in the code, why it break. There is a typo in the template for parser. Okay, now it works. Template for parser. I'm not sure which line you mean. If you can give me more specific line, then we can look at it. So anyways, when you run this code, it will produce the folder, and in that folder you will see like multiple runs, and each of those runs will right now it doesn't produce anything for you, but I just want to show you the big picture. So the big picture is that you will get a folder like this with the runs. So every time you execute this code, it will produce a run. And afterwards, you can use this command that I give you in the comments here. If I go inside terminal and I run this command and point to the path where I have the output of those runs like this, and run it by the Tensorboard log dir and show the output path of those my files that I have there, then it should produce nice results. Let's see. Yeah, so see, it says that you should open localhost 606. So, and if I open this directory, you will be able to do the same just in a second when we will add a little bit of code. So if you look here at our results, oh, this is nice. So you can see that we got about like 84% and then kind of converged here. So, sorry, here I should have the localhost 606. So this is how Tensorboard looks like. And you can see that you can store the accuracy by epoch by epoch. You can store the loss, you can compare them. So like you can compare different runs with each other. You can have also the images. Like, so the images are useful to have the confusion matrices. Like, I remember we had to make the prediction of the iris classes, right? So here we have 3 classes of irises of those flowers, and we see like which one the model predicts right now. This is a random stuff, but you can make it as like real stuff. Then also hyperparameters, you can compare different runs like patch size 16, 8, or some other things, like what is the best like results here with regards to the loss, with regards to the accuracy and other things. And you can also have really nice function of the projector, but I don't know why I don't see it here at the moment. See, projector. So the projector is for the internal representations or embeddings or other things that you can display in 3 dimensions or like reduce the dimensionality with some of the functions like PCA and others. Let's see, somehow the projector do not want to work for me now. Okay, I know, but it's not working. I use Safari. I use the Apple Safari, and that's why it doesn't work so well. But I just don't want to lose time. The projector looks, when you will run it on your own computer just in a second, it looks like the one that you had in the first slide, where you have these like data points, and they are clustered with their embeddings in the embedding space. So what it means that, for example, you have some kind of hidden state inside your like model, like logits or something, and you want to display it and see how well it clusters together or something like that. That's really nice tool that is built inside the TensorFlow. Okay, so let's start coding then. We added the arguments, and I see one person is active. Hope others are still alive. So I'm adding those parts of the code also to the Jamboard. So we did the fully convolutional model today, and now we're working on the data reporting of the with the Tensorboard. So first things first we need to add the summary writer. So the summary writer is the kind of the object or the instance of the class that will hold all of our data for this particular run. And we just make a simulated run here. So I mean, the output of this code, this will be just all of this will be simulation. And for the homework, you will have a really interesting task for working together with the pre-trained Torch Vision model and adding this kind of stuff to existing real model for Fashion MNIST. So you can kind of train the Fashion MNIST and see all of these functions, how they are useful for your case. So then summary writer. So this is just dummy code to demonstrate all of these features. So Tensorboard utils, there is a custom summary writer. If you want, you can also move this custom summary writer class to this same file that we have here, so everything is just in one place. Then logdir. So the logdir is the location where I want to store all of my information in regards to this run. So I highly suggest that you use exact same syntax as I do here, because what I want is I group the sequences. So the sequences are, for example, if I want to train all sorts of parameters with regards just to the fashion MNIST. So then I would call the sequence name fashion MNIST experiments. If I then train all of these with a different data set, then I would have different name, for example. Then the other part will be args run name. So I want to store for each of the runs separate folder. If I will not do this, then they will be mixed together as one run. And I don't want to have this as well. So we add this part of the code then. I also add this to the Jamboard so you can follow up on this. Maybe I should include line numbers. I will do that as well, including line numbers. And then we'll start adding some of these fun things here. Some of them will be really easy. In general, all of this stuff is quite easy. So here we are simulating the train loss and accuracy, right? So these are values that are not real values, they are just for the demo purposes. So here we want to add some scalar values. There are different ways how you can add scalar values. In this case, let's add them one by one, but you can also add all of them together. There are different ways. So one is that you can have add scalar like this. Then you choose the tag name. So normally I would say that you would choose here the mode, like this will be either like train mode or test mode, but in this case we can hard code this tag. So if I hard code this tag as train loss, and then have the scalar value of train loss, and then there is a global step. So the global step is the epoch. So we can also have the information about these values in between epoch. For example, for every batch as well. This is not limited to epoch, but we want this to be for the epoch only. So this part. So we add scalar value. We want also to add the accuracy, like that. Then we would like to see what is the dependence between our values and the hyperparameters. So the one way how this could be done is to have summary writer, add hparams. So this is the thing why we need the custom summary writer, because the default summary writer have bug here. So there is a hparam dict, and we can use the args dicts. Again, very good thing why we use the arg parse. We have the object or dictionary containing all of our hyperparameters, and we can very easily access them using this syntax. So we have this one, then we have the metrics dict. So the metrics are those that we want to track to compare different runs. And here probably we are interested in best accuracy. So we should store the best accuracy somewhere. Right now, just for the experiment purposes, we will use the same accuracy as let's say, train accuracy here. But we should also store the best one for all of the epochs, right? So that's one. And then also the name. The name we can get from args run name. So if we have multiple runs, we need some kind of identifier to compare the runs, right? And the global step is the epoch, like that. So now we are storing in that system these values. By the way, at the end of tutorial, I will try to run this and show you this projector thing that I didn't show you in the Chrome browser, because like Safari doesn't work with this, unfortunately. Maybe with Firefox I could show it. Probably with Firefox it works. So I added also this part of the code to the Jamboard. So let's make a small pause here and wait for everybody to catch up. So I will ask a question in the chat. Is the code done till line 59? and all is clear, plus minus, and working. So W say that if you are working on it, it means working on it. So I would know if should I wait or proceed. So I also don't want just sit around, and if you don't do the work also yourself. If you do the work right now, you get 100 points because you need to submit the working example from the classwork as well. Kristaps saying, good catch, good catch. So the epochs is missing, right? That is also a hyperparameter. So we should add epochs as well here. So the epochs means how many epochs do we want to train our model. So let's say we want to train 10 epochs, but maybe we want to train 100 epochs. It depends. Like for example, everything converges already in 10 epochs, then we don't need 100 epochs. And usually you also have early stopping. That means that there is some specific code that you can use to stop the code after you have a convergence of the test loss. So that's a good feature to have later. But thank you for question. Thank you for pointing out that I missed the epochs. And now it should work so far. Of course, everything is not yet done. So I see that one person has yet finished everything. Let's wait for maybe some other. And then we'll do these few to-dos that are on the bottom part, and then we'll be good to go. Okay, good. I see that at least 2 people are active. So this is again dummy code here. Usually, like if you already are, like there is no batches so far, so that's why here there would be some kind of batches. So here again, if you want to make it even more dummy code, we can have here some simulated batch size or whatever. But it's not necessary, you can leave it as it is. So here we need to calculate the confusion matrix. The confusion matrix is just a really nice way to display the accuracy, to ensure that we have like what is the false positives or false negatives, like in what direction our model is more biased. Like the best way is then when the true label matches the predicted label, and then we have the trace of the matrix with a 100%. Otherwise, we want to fill our matrix one by one. By the way, maybe I should show you one resource before doing this, because I don't really have time to go in depth with all of these things, unfortunately, because this will be actually the last session where we talk about the classification tasks, and then we move to more difficult other types of tasks. because like all of this course is like compressed and like we don't go in that depth. But so let me quickly share some material with you. Why it's not opening? Hopefully I can open it somehow. So you can find information about confusion matrices, and especially confusion matrices are very interesting when we think about multi-class confusion matrices. If we think about the just binary classification where we have just, well, is this class what we want or not, then this is really simple. When we have the multi-class classification, then this becomes really valuable and interesting. For example, we can like kind of understand which classes are more similar to which other classes. And we also can calculate F1 score for multi-class example using the this confusion matrix. So this is a confusion matrix. Let me check if I'm sharing the screen right now. Yes. So the best case when we put the numbers here as soon as we classify something as in this way. So for example, the true class is apple, and our sample predicts that this is an apple. Then we +1 this cell. So if the true class is apple, but the model predicts that this is an orange, then we +1 in this cell. So, and the so on goes for all other classes. For example, if the true class is orange, and this is actually an orange, then we add like 2 + 1, there will be 3 here. And if we find another example like that, then there would be 4. And we decide which class it belongs by using the argmax, or just the maximum probability, right? For every sample that we run through our model, we have 3 probabilities, right? Either this is an apple, orange, or mango. And like so in this data set. And then we decide which it will be by the highest probability. If we say that 99% this is a mango, so then we say that check if this is a true class. If this is a true class, so if the real value is also mango, then we add it here. If the real value is actually if the real value is actually something else like the apple, then we add it here, because the predicted value was mango, but the real value was apple. So we add here. So we count how many samples fall in each of these cells. After we count all of these cells, then we can decide on which are the true positive samples. So that is the most easiest thing, because for the apple, the true positive samples are here, just in this one cell. Then the true negative samples are these ones that are like 2 plus 3 plus 2 plus 1, so all of this region. So if we sum all of this region together, those are true negative samples. So that means that the model predicted something so it did not predict the apple where it should not predict the apple. So then the false positives, so this is where it predicted that this is an apple, but this is not an apple. So we see that we predict apple here, but it's not an apple for these two things. So we combine them together, we sum them. So the same thing for false negatives, again here. Now we have 4 metrics: the number of true positives, number of true negatives, number of false positives, number of false negatives. And we can plug them in different kind of functions. So one very common metric that you use is called F1 score. So you can plug it in here and you get the value, like the kind of like accuracy, but better than accuracy, because now it contains information also about the situations where it's not only the true positives. So this is much better way to calculate the accuracy using some kind of metric that is sensitive to variations between different classes. So let me ask about this. Is it clear? Is it clear why confusion matrix is good? Also, you can see that if the samples of like the numbers are high in between some of the two classes. Maybe they are too similar, or there is like dataset problem or something like that. So do you understand why it's good or not? Okay, great. We have one plus coming in. So I think we at least have 2 active people yet. Great, very happy about that. So this is very nice way to understand what your model learned. So let's move back to our dummy code and complete those few tasks there. So the dummy code says that we should calculate the confusion matrix from our dummy predictions. So the dummy predictions we can easily get out like this. So let's see. So the index for the ground truth, this is the torch argmax of y over dimension. So the dimension is the probability dimension, that is 1. 0 dimension is the batch size. So then the data numpy, so this is 1. Then the y prim, so this is our predicted values that we can also take there. By the way, this is a dummy code, but this part can be used also for your real code. I mean, this is not something out of the blue. So here we can go over all of our indexes in the batch. So let's see. So IDX sample in range of, so our batch size. So here there is a batch size, but of course we cannot rely on that in real case. In real case, you should take your batch size from size 0, sorry. So here we have the confusion matrix. And we select the correct cell position. So we need the cell position that is correct for each of the samples. So IDX sample by IDX prim, IDX sample. And what we do is we just add 1. Of course, later you can normalize it, right, and make it as probabilities, right? Like this is like probability of mixing that class with other class. So that's great. Then the next thing is we need to add this image to the Jamboard, to the Tensorboard. So we can have the figure here, plot figure. So this is a holder, like a pointer of our image that we can then use to save as a figure. So this will be marking that all of this part will be included. Okay, I need to also delete this show. I don't need the show here. I don't know why it was there. Actually, that should be deleted as well from the template. Then let's add to the figure here, summary writer, add figure. And here we have the tag, confusion matrix. Figure will be the fig here, and the global step, of course, will be our epoch, right? So that's great. I will add this part also to the Jamboard. And we're almost done today. So you will have similar task in the homework. You will have like pre-trained real model, like the pre-trained model from Torch Vision that I will include in the template. And you will need to add all of this stuff around it to measure the confusion matrix, to measure the losses, accuracies, and everything in between the epochs. And that will be really useful stuff also for your future work. So I added that part to the Jamboard, and now we need to do the last things. So here we are generating the blobs, like 100-dimensional, 128-dimensional clusters of data that we want to add to our summary writer here. Add embeddings. So for example, this could be like voice identification, embeddings, face in the embeddings, and all sorts of things. Also, you will see next week we are working with autoencoders, so the autoencoder embeddings also can be added here. So here we can have the classes to list. So this will just make the colors, so the colors for embeddings that they would be like from this class's value. Then the tag embeddings, and the global step, of course, epoch. Then if we want, then we can also have the flush. So the flush means that at this moment I want to write everything in files and not wait till the summary writer thinks it's a good moment to write in file. So, and then at the end also would be nice to close the summary writer. So that's about it so far. I also will add this to the Jamboard. And meanwhile, while you catch up and it's almost end of the session, I will try to run the same stuff on the Firefox, hopefully to show you that Tensorboard. So is the Tensorboard working? Yes. The nice thing is also, if I run this code now, so let me see. Yeah, if I run this code now, by the way, I added the code to the Jamboard, don't worry for that. So if I run this code now, the Tensorboard will update automatically. I mean, like, okay, I run the wrong code. So the Tensorboard will show new run while it's open. So I mean, like, you can run your results and see in real time what is the output of your results, and you can run like many runs in parallel and see all of those outputs immediately in the Tensorboard. So that's really nice feature. So let me try to find with the Firefox to open that link, and that will be the end for today. On localhost 6006. By the way, you can change the port number as well. That's not an issue. Let me see. Will the projector work for me? Maybe it was not related to the Safari. Oh no, it was. Nice, nice, nice. So let's end with nice pictures. So full screen here. So you see, if we run those embeddings inside the projector, we get really nice pictures here. We can have colored them by the classes. So these are those two clusters of 128 dimensions projected only on 3 dimensions. We can project them also on 2 dimensions like this, and we can turn off the L2 norm. So, and then if you project in 2, it looks like that. We can use also all sorts of very interesting ways to reduce the dimensions. So one is TSNA algorithm. Yes, yes, nice to see you, Dimitri, on the live call. So yeah, this is something definitely I would advise to use also for other projects, not only embeddings. You can use that for the hidden states of all sorts of things. You can use that for the kind of like you can add that each of these samples contains also input image, and then you can compare if that hidden state is actually similar to other hidden state, but just by looking at the images. So that's really useful thing. I think from the Tensorboard, the projector is one of the most useful things. The second useful thing I think is images, that you can scroll over the epochs like this using this bar, right? And otherwise, like with the hparams, it's sometimes better to use the just simple CSV files. Okay, let me just double check if I can get some other visualization, because it took me so long initializing and nothing happens. Anyways, if you try it yourself, you will see nice pictures. With the linear projection of the PCA, it works immediately because you just calculate the eigenvalues. That's easy stuff. But with others, it's a little bit longer time. So anyway, that's it for today. I know it was a little bit hectic in beginning. Sorry for that. It was like really long day for me. Next time I will prepare the templates a little bit better, so we don't need to have some bugs in templates. I will also update templates in the classroom for those poor guys and girls who will do the homeworks later. And you who did this in this real-time session, then please submit them, and we can you can get your points and be done with it. So that's it from today.